Everyone, welcome back to Chemical Engineering and Aspen channel. Today we will be simulating heat exchanger on Aspen Plus. In our previous video, we had simulated the heat exchanger on Aspen Hysis, and now today we will be doing the same exercise on Aspen Plus. So if you have not subscribed to the channel, please subscribe to the channel, click on the bell icon to get all updates related to this channel. So first thing is to add the components, and the method is same as that of the Aspen. So we will add ethanol as the first component and then water as the second component. The next thing is to select the property package, the suitable property package. So we will go to the methods in specifications. We will select the base method as NRTL. And then we will click on this next button and estimate using Unifac. We will tick it and then we will run it. And you can see that the results are available. It means there is no issue over here. There is no warning. There is no error in the properties tab. So we will go to the simulation environment. And once we go to the simulation environment, we will first select the heat exchanger. Obviously, this is the the heat exchanger which we will be using for our activity, the two stream concurrent or counter current heat exchanger. So we will click on it. We will paste it over here. Then we will do the streams connection. This is the hot inlet. This is the hot outlet, cold inlet, and cold outlet. And control A, control B to just align the PFD. We will say S1 as H in, S2 as H out for proper nomenclature so that we can identify it properly. Then S3 as cold in and S4 as cold out. And B1 is replaced as HEX, which is the heat exchanger. Now, once we have defined the flow sheet, we have drawn the flow sheet, we have to next define the stream properties. So we will define H in this one and C in these two streams. So double click on it. And if you remember, we had specified the vapor fraction and pressure. So we will be defining the same over here. We will select vapor fraction instead of temperature. Pressure is 300 kilopascal. Vapor fraction as 1 and molar flow rate as 50 moles per hour of ethane. So how we can ensure it? We will go to the small fraction, eth ethanol as 1 and water as 0. Then we will define the C in 25 degrees centigrade, 300 kilopascal, then water flow rate as 1000 and mole fraction of ethanol as 0 and water as 1. Then we will go to the next, click on next, and we will go to this heat exchanger. Obviously, in model fidelity, it is a shortcut heat exchanger which we are simulating, and the direction is counter current. So we will come here. Obviously, the calculation mode is the design mode, no rating, no simulation. And in specification, there are different properties available to us. We have to make sure that the outlet temperature of water is 40 degrees centigrade. So water is actually the cold stream. So we will have to define the cold stream property over here. Although you can see there is a long list that hot stream outlet temperature decrease, hot outlet minus cold inlet temperature difference, and up to so on. So we will define the cold stream outlet temperature as 40 degrees centigrade, and the minimum temperature approach, obviously for the ambient temperatures or above ambient temperature processes, we will usually define the temperature approach as 10 degrees centigrade. Also, we have to define the pressure drop. So we will go to this pressure drop tab. And if you remember that the pressure drop was 10 kilopascal on both sides, on both hot and cold side. So we will define in the negative. Once we define in the negative, it will automatically consider the pressure drop minus 10, but obviously it is kilopascal. Then we will change the side, cold side, minus 10 and kilopascal. So once we have defined all the required things, this run button is now active. So click on this run button and you can see the result will be available to us. And if we right click on it, we will go to the results. You can see that 108.721 3 bar vapor fraction 1, it has gone to 107.676. 2.9 bar, obviously there is a pressure drop of 0.1 bar, vapor fraction 0.392436, and accordingly from 25 to 40 degrees centigrade, and corresponding heat duty is calculated over here. If you go to the heat exchanger details, you can see the calculated heat duty, the required heat exchanger area, the average UA, the LMTD, all these values are calculated from this design activity, and you can see that this is just a shortcut type. This is not a regress type. We are not calculating the shell passes, or we are not calculating the tube types or tube bundles or different properties related to heat exchangers. This is just for the initial information so we can start our work and then we can do the rigorous design based on it. So this is how we simulate the heat exchanger in Aspen Plus. I hope you have understood all the aspects of this lecture. If you have any queries, feedback, suggestion, please provide it in the comment box and I would be happy to answer it. So that's it from today's lecture. Thank you so much. Please do watch, like, share the video and subscribe to the channel. Also click on the bell icon to get all updates related to this channel. Till then, it's goodbye. Stay tuned for more exciting videos on this channel.